Hello, students. We are just out of operations on whole numbers. And so we're going to move into chapter 4. And chapter 4 is a little bit different. It's called number theory. And the idea is that we get into some key concepts about how numbers work with each other that are actually very helpful as we move forward. So we're going to talk first about divisibility. And you'll get to see right here off the bat the Common Core component. This one starts at grade 2. We're talking about even or odd. And so, for example, understanding what even and odd numbers are. We've done a little bit with this. An even number is a whole number as a remainder of 0 when you divide by 2. So that links back to division. An odd number has a remainder of 1 when you divide by 2. And those then must be the only options, because if we're dividing by 2, you can have a remainder of 0 or 1. We could not have a remainder of 2. Remember, the remainder has to be less than the divisor. So anyway, that's kind of the components that we want to talk about first with odd and even. And then we link it back to the idea of division with the concept of what's known as divisibility. And there's 3 different ways that we kind of say it. We say m is divided by n. We say n divides m. So that is more active, and one is doing one to the other one is a divides. And that's the piece that we'll see right here at the bottom. 2 divides 12. Okay, so that means 2, if you want to think of it that way, goes into 12 evenly. So when we have a remainder of 0, then the remainder of 0 that means it divides evenly. So if you were looking at, say, 12, and you were saying, hey, does 5 divide 12? And this is the vertical line. It's a kind of a vertical line. It means divides. So 5 divides 12. This is now a statement going back to chapter 2. So this statement would be either true or false. So when we say 5 divides 12, then what we're looking for is, by definition, is there a way to write 12 is equal to 5 times some unique number? That means there has to be one and only one number that would work. Okay. So let's see if I can jump over here, get rid of that. Okay, so there has to be a whole number that could fit in here and work. What number multiplied by 5 gets me to 12 right on the nose? And there isn't one. So in this case, what we would do is we would say 5 does not divide 12. Okay, and the reason we could actually write it out, we could say, well, 12 is actually equal to 5 times 2 plus 2 additional, 5 times 2 being 10, plus 2 more to make the 12. So this shows why it doesn't work. And the reason is, once again, we need the remainder to equal 0 is what we need in order for something to actually divide. So that's the idea of divides, kind of as a verb, something actively divides it. And so again, here's our definition of divides. And once again, it says you cannot use 0 as a divisor. I again think we should scribble this out because you can include it in there. There just would not be an answer for those, and that you would say is, oh, therefore there is no answer. So I would say that it does not divide, and because it would be outside of the definition, it would then be called undefined, and you probably heard that from other classes. Okay. So if it does divide evenly, remember, that means I can rewrite it as a multiplication problem. And if a multiplication problem comes up, we could say one is a multiple of the other, or one is a factor. So those are the terms that relate back to multiplication. So A times B, let's see here if I write that out. So if I say 3 times 5, and we know that is equal to 15, remember the number on the side is the product, that these numbers over here are factors. And we could also say that 15 is a multiple of 5. Could also say it's a multiple of 3 because, again, those are the factors that are there. So here's the words that we use: factor, multiple, and we would also say 3 divides 15. We could also say 5 divides 15. Again, because if it divides like these do, I can rewrite it so that I can show a single multiplication with no remainder. Right, let's clear those off and move on to the next component. Awesome. Yeah, now there is a little note here, which I think is really important. So in math, you see this, I'm not gonna lie, there's times where the notation can be a little tricky. So for example, if I wrote this 12 with a sideways piece with a 3, this is actually saying 12 divided by 3. And that, the answer to that is a number, okay? If I wrote it the other way, where I wrote 3 vertical line 12, this is not a number. The answer to this is not 4. The answer to this is true, because this down here, this piece is a statement, not an operation. An operation is kind of saying, hey, I'm going to divide numbers and I'm trying to find the result. And that is not what we're doing here. We're simply saying 3 divides 12, and you would say true or false. Okay, and you'll see that in the questions that are being asked. You have to classify these statements as true or false. Every one of them should have a reason why, but we would classify them as true or false. Okay, so let's take a look down here. Suppose we have 1 pack of gum. We know the number of pieces, A, is divisible by 5. Okay, now we have 2 packs of gum. The total number of pieces of gum is still divisible by 5. That kind of makes sense because each pack is. And the same is true if we had 10 packs or 42 packs or any number of packs. So n packs, which is kind of that general piece we talked about at the beginning of the term, like with the nth term, we're just now using it as a general number. So this is a very interesting and fun piece. If you know that 5 divides a number, then, so this is if then, this is conditional. Oh, thank goodness, we get back to some conditional pieces. So we generalize it here. So if D divides A, and A is, oops, sorry, and N. D divides A, and N is a whole number. Then here's my then statement. Then D has to divide N times A. Okay. So again, this is the general statement. You'll notice there's a lot of letters in here because we're talking about a general piece. But picture this. We know that 3 must divide 9 because 3 times 3 is 9. And I'll pick another whole number. Let's say 21. Okay, well, 21 is a whole number. Then what they're saying is if you know these two pieces, if both of those are true, then you also know for free that 3 has to divide 9 times 21. So 9 times 21 is 189. So 3 must divide 189. Guaranteed. That has to happen. Now, if you wanted to, you could break it down and say, well, this would be the same thing as saying 3 divides 9 times 21, and it is. But you notice 3 divides the 9 perfectly. Now, I chose a second number as a whole number that also 3 divides evenly. But what's great about this is it doesn't matter what whole number you choose. You could have chosen 23. 3 does not go into 23 at all. And guess what? It still works. Now, instead of 189, you would say 207, and it would absolutely still work. So this is what we know in math as a theorem. Now, a theorem is a statement that we believe is always true, and we can prove it. So when we look at something like this, if I was trying to prove to you that this statement is always true, then what we would do is we would start with the if part and try to show the then part must be true. Remember, the only time this would be false is if you meet the condition and fail the conclusion. So what we're going to try to do is show that if we assume that the first part is true, we're going to try to show everybody that the second part cannot be false, which means that the statement itself must be true all the time. Okay. So let me jump up here, try to throw in a little bit of white space. Actually, maybe I'll just share a whiteboard screen real quick. Okay, here we go. Okay, so what are we talking about? Let's do this. So what we're going to say is we know, here's our statement. If D divides A and N is a whole number, then D divides N times A. Okay, that's what I'm trying to show. All right, well, let's start by assuming these components are true. So what we're going to say is D does divide A, okay, which means, so A has to be some multiple of D. So I'll just pick some multiple, I'll call it C. And remember, by the definition, C has to be a whole number. Now, next up, N, we know N is a whole number because that's one of the pieces right up here. That's what we're assuming to be true. Right. So now let's take a look. We're going to take the original equation right here, that A is equal to D times C, and I'm just going to multiply both sides of that equation by N. So what I have is A, I'm going to leave a little space, D times C, and then I'm going to multiply both sides by N. Because if the original equation is true, multiplying both sides by N is still going to be true. So what I now have is a brand new equation. I have A times N is equal to D times C times N. And now I have D multiplied by some value, and off to the side, C times N is a whole number because the whole numbers are closed under multiplication. That means if I multiply two whole numbers together, and remember I had a whole number called C and a whole number called N, if I multiply them together, I get another whole number because it's closed. So now this quantity is just some whole number. We've shown it's a whole number. And if it's a whole number, then by definition, D times a whole number means that D divides. So my final response would be that D has to divide A times N because I found a whole number that you can multiply by D and get back to A times N. And I'll even put a little therefore here. D divides A times N. So take a look at what we did. We started with the two components of the statement, which would be the condition. So I assume the condition is true. And what I did is I showed you, based on that being true, the conclusion also has to be true. And this is what we would call a proof. We don't want to do proofs by examples where we just list a whole bunch of things that we know are true. We want to do a proof that guarantees that it always works. And that's what we just did. Okay, well, let's jump back to the textbook. Okay, and I believe if you kind of flip the page here, you'll actually get to see, here's this. They say to generalize this notion, here it is. But now they also talk about the theorem can be stated. They actually, I think this is one of the homework problems they ask you to do that. So I'm glad I showed one of them to kind of walk your way through the whole piece. But now what they're going to say is, hey, what if one pack of gum was a multiple of 5, another pack was not a multiple of 5, and we pushed those together? Does that work? And that's the next kind of theorem. So to kind of explore these theorems, what do you think? If we know that A is a multiple of 5 and we know B is not a multiple of 5, then if I push A and B together, will 5 go evenly into all of them? And we'd have to say that's not going to work, because I could take all of the A pieces and break those into 5 groups. But if I tried to do the same for B, I wouldn't have enough to make them into 5 groups. So this is now a new theorem. So if it works for one but not the other, when you add them together, it does not work. And they added a now try this, which I think is a really good one. What if you had two numbers that do not divide? What if you push those together? Will 5 now divide the whole piece? Okay. And it says determine the truth of this statement. Remember, a statement is either true or false. And so it might depend on the A and B. So you might be able to find times when it's true and find times when it's false. But I need you to remember, if this is an if-then statement, if you can meet the condition and fail the conclusion, the statement is false. Okay? Doesn't matter if it worked 10 times. It matters that it didn't work just one time. Counterexample. Okay. So as you're looking through here, what we're going to see is a list of theorems about divisibility. The first one is if it divides A and it divides B, guess what? You can push them together. It does divide the sum. If it divides A but it doesn't divide B, it does not divide the sum. If it divides A, divides B, and A is bigger than B, because we're still thinking about whole numbers for our students, then D would divide the difference. Okay. And if it works for one but not the other, then it doesn't divide the difference. And anyway, and basically the last piece down here is saying if it works for one but not the other, then it will not divide the difference, no matter whether it works for the first part, the minuend, or the subtrahend, the first part of the subtraction or the second part. Doesn't matter. Okay. The proofs of several theorems are left as exercises. They give you theorem 4.2a and b down here. Again, what they're going to say is part A, if it works for both, how do I know it works for the sum? And they go through it. They say, oh, because D divides A, so that's part of the condition, then A is equal to M times D for some whole number. They called it M. And if D does divide B, which again is part of the condition, because the condition is the and statement, both has to be true, then B is equal to N times D, which is again some unique number M. And then what am I trying to find? I'm trying to look at A plus B. So if I do A plus B, that would be MD plus ND. I use the distributive property to factor something out. And what I've got here is I've got a unique number, M plus N, which is an element of W, because the whole numbers are closed under addition. And so I now can show that A plus B has to be divisible by D. All right. So there we go. Same concept for the other one. I'll let you look over that one if you want. Classify statements as true or false. These are just now applying the theorems, right? Applying the theorems. Now, if a theorem is not listed there, you have to think about some counterexamples. Right? Okay. So let's see here. Coach Edgerton bought 9 pairs of shoes, gave each, make sure every pair gets a shoes, came up with a receipt. The last digit was erased. So I know it was 530 something, but I know that it's divisible by 9. So if you divide 530 by 9, you get something with a remainder. The remainder is 8. So if you were to add one more dollar in there, you know it would be divisible by 9 evenly. So 531 would be the total. So you can actually figure some things out even if you don't have complete information. Let's see here, divisibility rules. This is a calculator with an INT division button. Some of you have these, some of you don't. An integer division button gives you the quotient and the remainder when you do the division. Again, not all calculators do. So when we start looking at divisibility rules, we start looking at ways we can show someone that something always has to be divisible. Now, if you don't have that int division button, your goal is going to be to use those theorems. So if I look at the number 1734 and I ask, is 17 divisible into 1734? My goal is going to be to try to show that it works for one of those theorems. So break off something like 1700, where you know 17 has to divide 1700 evenly, and then leaves me with a 34. So I know it works for 1700, and then I try 17 into 34, and it does go in evenly twice. Remember, I don't care how many times it goes in, I just care that it does. Then I would be able to say this is true. Okay. Now you can do that for any group of numbers. So you could ask, does 7 divide into, I'm going to use the same number because we'll see if it works, right? So this number 7, I'm trying to think of something that goes in evenly into 7. I think 7 goes into 14. So I'm going to make 1400, and I'm going to leave some stuff over here. And I know 7 goes into the first number. I don't know about the second one. What I'm going to do is I'm going to break it down a little further then. Why don't I break this down into 280 plus 54? And I know 7 goes into 280 because 7 goes into 28. And then 54, maybe I'll break it down into 49 with 6. But you could also say 7 does not go into 54 right away if you need to. But it goes into 49, it does not go into 6. So does it work for the whole thing? And I would say false. Okay. Now why? Because it works here, it works here, it works here, which means I've got a sum of numbers that it works for, but one number that it doesn't. As long as there's exactly one number that it doesn't work for, we have a theorem, and that's theorem 4-2b. Okay. So that's part of what we're doing in this section. So when we start looking at divisibility tests are kind of grouping things together. So they're trying to say, can I know that a number divides without having to do all that work? Maybe there's a shortcut or a quick way. And for students who are kind of looking at numbers, there are some really quick ways to decide whether numbers are divisible by 2. Okay. Now, what I want you to do is we're going to talk about using these theorems. So there are divisibility tests for 2, 5, and 10. Now, what I want you to notice here is that 10 is 2 times 5. So whatever test you come up with, if it's divisible by 2, right, if 2 goes into it, right, then you'd still have to check to see if something else goes in. But if you know that it's divisible by 10, you guarantee that it's divisible by 2 and 5. So let's talk about what are the rules for 2, 5, and 10. So again, if it works for 10, then it works for these other numbers. Let's talk about divisibility by 2. Well, I know that any multiple of 10 is divisible by 2. So if I had 3, 4, 6, 2, I guess I'll do this one. No, I'm not going to do 2. I'll end it here with an 8. So what I know is if I broke this number up into 3, 4, 6, 2, 0 plus 8, the same theorem would hold. This number right here is a multiple of 10. So this guaranteed is divisible by 2 because 10 is divisible by 2. And this is theorem 4-1. And now the 8 over here, all I really have to look at is the last digit. Does 2 go into this last digit? And it does. And so that's by theorem 4-2a. If it works for both pieces in a sum, it guaranteed works overall. So this is a really convenient rule then that you could be kind of showing to students. All of these other digits are great, and it really doesn't matter what they are. What we end up checking, because they're all multiple of 10, basically. So all I end up checking is the last digit. So if I want to check divisibility for 2, I check the last digit. And remember, this is a multiple of 10. So the same thing is true for 5. 5 goes into 10. That's theorem 4-1a. So if you want to check whether this number here is divisible by 5, we really only have to check the last digit. So if 2 divides the last digit, then it divides the whole number. If 5 divides the last digit, then it divides the whole number. But if it doesn't divide the last digit, it doesn't divide the whole number. And lastly, the divisibility for 10 would mean the same thing. 10 would have to divide the last digit. And there's only one digit that works for 10. 10 has to divide 0. So that's what you're going to see as you look down into these theorems here. They call them theorems, but really these are your divisibility tests. A whole number is divisible by 2 if and only if the unit's digit is divisible by 2. Divisible by 5 if and only if the unit's digit is divisible by 5. And each one of those we kind of gave a reason why. And lastly, you have a divisibility test for 10. It's divisible by 10 if and only if the unit's digit is divisible by 10. And it says that is if the unit's digit is 0, because that's the only one that works there. So now here comes the fun part, at least for me, when you start thinking about what about other numbers as we kind of grow up. So 2 times 5 gives me 10. If I look at the number 4, 4 is 2 squared. If I try to relate that back to my number bases, then really 4 times 25 would get me to 100. That's one of my perfect numbers in my number base. Got it. So 2 squared times 5 squared is equal to 100. So this gives you a way to test for 4 and for 25. And because it's multiples of 100 that are now guaranteed to work, you can take any number to see if it's divisible by 4, and you would check just the last 2 digits, because everything else multiples of 100, you can peel those out and get those for free. So they say 3458. Why don't we do 3456? And we're going to say, does 4 divide this number? So what we do is we peel off the multiples of 100 because we get those for free. And then I'm left with 56. Now you can look at 56 and say, shoot, maybe you can see it there, but if not, hey, do yourself a favor, pull out something that does work for 4, like 40. Right? If you can't see the 56 going in perfectly right away, that's okay. Find another number, break it down to one that does guaranteed work, and then you're really only checking this last piece. And so yeah, it does work. So what this theorem is basically telling you, and this is why I think these are kind of really nice, is you look at a 4-digit number, and really you can look at it and say, this part right up here, I don't even care about to know whether 4 divides the whole number. It's only the last 2 digits. And that's what you're going to see in the divisibility test. It says the last 2 digits. Right? The divisibility test for 8, and honestly, you actually could continue going with this. 8 turns out to be 2 times 2 times 2, which is 2 cubed. Oh, nice. So 2 cubed, I would just need 3 decimal places, or 3 digits, because 2 cubed times 5 cubed would give me 10 cubed, or 1,000. So basically now I'm peeling off groups of 1,000 when I'm checking 8. So you'll see questions like this quite a bit. It says determine whether this number is divisible by 2, 4, and 8, and determine whether the next number is divisible by 2, 4, and 8. So just remember, if I'm doing 2, does 2 divide 83026? 2 goes into 10. So I draw my little cutoff line, and I'm really only looking at the last digit. Does 4 divide 83026? Okay, 4 goes into 100. So I'm peeling off all the hundreds, and I'm really only looking at the last 2 digits. Does 4 evenly divide 26? And the answer is no. So this one would be false. Does 2 evenly divide 6? And the answer is yes. So that one would be true. Now here comes the fun. If 4 did not divide this number, 4 times 2 is not going to divide that number. All right. So anyway, we could say 8 does not divide 830. Oops, get rid of that. 83026, because I'm looking at the last 3 digits, and 8 does not divide the last 3 digits. So that'd be false. All right. Very, very, very cool stuff. For me, anyway, this is super cool because now you get to see kind of where it goes together. They kind of group these together. So notice you have a Venn diagram now listing all these connections. Numbers that are divisible by 2 is kind of the biggest group. There's a smaller group that are divisible by 4, because not as many are divisible by 4, and a smaller group that is divisible by 8. So this is kind of an interesting piece then. Take a look at this with if-then statements like we did back in chapter 2. If a number is divisible by 8, then it must be included in here because it's inside the circle, and it must be included in here. So if 8 divides a number, then 4 divides the number, then 2 divides the number. So you get all those other pieces for free. So that's pretty awesome. Okay. Divisibility tests for 3 and 9, they turn out to be the same. And there's a reason for it, because when you look at our number base of 10, we could rewrite 10 as 9 plus 1. And 3 divides 9, or 3 divides, and 9 divides 9 as well, I guess I should say. 3 divides 9, and 9 divides 9. So really, the tests for 3 and 9 turn out to be the same test. And if it's 1 digit, you just look at the last piece. If it's more than 1 digit, what you do is you break up chunks that are divisible by 9. And it turns out every place value, like 100, is 99 plus 1. Well, 9 divides into this perfectly. 1,000 is 999 plus 1. And guess what? 9 divides this one perfectly. So what you end up doing because of the distributive property is you end up with this beautiful number that you started with. You break off all the 9s, and what you're left with is just the sum of the digits. 5 plus 7 plus 2 plus 1. So it seems a little weird, but if you want to check to see if 3 or 9 divide into a number, you have to add, you just add the digits. Let's see, so 2 plus 1 is 3, 3 plus 7 is 10, plus 5 is 15. So yeah, 3 does divide 15. So guess what? 3 does divide the whole big number perfectly. Right? So that's kind of a fun little piece there.